Our next topic is going to be looking at inverse trigonometric functions. We're first going to review what we know about inverse functions in general, back from Chapter 1. We're going to discuss some issues with defining an inverse to the sine function because it's not totally straightforward at first. Then we're going to show how we restrict the domain of the sine function to enable us to create an inverse sine function. And then we're going to do an example computation. Alright, so here's what we know about inverse functions. So suppose f is a function. Here's what we know about its inverse function f inverse, if indeed the inverse function exists. First of all, we know what the definition is from a computational point of view. If we do one of the functions, then its inverse, what they do is cancel each other out, which means that if we start with x, do f of x, and do f inverse of that to get f inverse of f of x, that gets us right back where we started at x. And if we do it in the other direction, the same thing. F of f inverse of x is also equal to x. And again, what this is telling us is that f and f inverse cancel each other out. The other thing we knew is that if we had the equation y equals f of x, that means that when we solve for x, we get f inverse of y. And what that led us to think is that when we got to the graphs of inverse functions, the graph of f inverse is exactly the same as the graph of f. The only difference is we switched the x and y axes. And then we finally were able to determine when a function f has an inverse just by looking at its graph. And what we came up with is something called the horizontal line test, which says that f actually has an inverse precisely when every horizontal line intersects the graph of f at most once. So let's go ahead and apply this to our trigonometric functions, starting with the sine function. So the first question we might ask is, does f of x equal sine x have an inverse? We can take one look at the graph and say, I don't think so. That horizontal line, the orange one, that's going to intersect the graph of the sine function infinitely many times. Clearly, that fails the horizontal line test, which means we have no inverse. So we could just walk away and say, yeah, sine of x has no inverse. Why even try? But what we're going to do is we're going to make some adjustments to the graph of sine of x so that we can actually have an inverse. And in fact, if we ignore enough of the graph, we can actually make a sine function with an inverse. Now, it won't be the sine function with the entire domain. It'll only be with part of the domain. So let me give you an example. Here's part of the graph that I turned orange, and it goes from the top of the graph there at x equals pi over 2, and y equals 1, and goes to the bottom of the graph at x equals 3 pi over 2, and y equals negative 1. Now, if I ignore the purple part of the graph, what we have is, if you ignore the purple part of the graph, the orange part of the graph actually does satisfy the horizontal line test. If I draw any horizontal line, it'll hit the orange part of the graph exactly once. So what that tells us is if we make the domain of the sine function just between pi over 2 and 3 pi over 2, then we can define an inverse. But that's not the only part of the graph that we can do that to. Right? If I make the part of the graph orange between negative 3 pi over 2 and negative pi over 2, that part of the graph also satisfies the horizontal line test. And so we can make an inverse sine function out of that as well. So there are actually infinitely many ways that we can define an inverse sine function. And what we have to do is just choose one of those ways and agree to it, and then that's what the inverse sine function is. Now, of course, in an ideal world, you and I would agree to that interval ourselves, whichever ones we think is our favorite. Unfortunately, a bunch of mathematicians beat us to the punch, and the one we're going to use for the standard inverse sine function, and that's called the arc sine function, that is going to be the angles between negative pi over 2 and positive pi over 2. Now, is that superior to one that we might choose, one of the other ones that we did in the previous slide? No. But we have to choose one. That was the one that was chosen for us, so that was the one we're going to use. Sorry, we were born a little bit too late. And here's the part of the graph that we're going to look at. So the left part of that graph is down at x equals negative pi over 2, and the right part of the graph is at x equals positive pi over 2. And notice that if we draw any horizontal line, it's going to intersect that graph at most once. All right, so now let's consider the equation at y equals sine of x and see if we can gain any understanding about the inverse function. So first of all, in order to figure out what the domain of our inverse sine function is, let's think of our domain and range of our sine function. So for the domain of our sine function, we think of x as the angle for that sine function, right? And for the range, the output is sine of x. We think of that sine of x as either, if we're thinking right triangle, it's going to be the ratio of two sides of the right triangle, in other words, or we can also think of it in terms of the circular function as the ratio of the y-coordinate to the radius of the circle. Now, if we want to flip that and actually think about the arc sine function, well, remember, one way of taking y equals sine of x and taking that same equation and thinking of it in terms of the inverse function is solving for x. So x is going to be arc sine of y, right? That's one of the ways that we understood inverse functions. So remember, that arc sine of y, that is our angle x, and for the arc sine function, we're only looking at angles in the first and fourth quadrants. In other words, angles between negative pi over 2 and positive pi over 2. And therefore, arc sine of y is going to be between negative pi over 2 and positive pi over 2. So let's look at the domain for the arc sine function. Well, the domain is going to be y. And guess what? That y is still the same y as we had in y equals sine of x. So remember, back in the old days when y was sine of x, y was the ratio of the sides of a right triangle. So our inputs for arc sine of y, those are going to be ratios of the sides of a triangle, or the ratio of the y-coordinate of our point on the unit circle to the radius of the unit circle. Now our range for arc sine, that is arc sine y is equal to x, right? So x was the angle, so arc sine y itself, the outputs are going to be angles. So what happens with the arc sine function is the inputs and the outputs get flipped. It used to be for the sine function, the inputs were angles, the outsides were ratios. Now, for arc sine, the inputs are ratios, the outputs are angles. And if you want to see what those angles look like, again, those angles can only exist between negative pi over 2 and positive pi over 2. So negative pi over 2 is way down there at the bottom of the unit circle, or bottom of the circle, and pi over 2 is at the top of the circle. And so the angles that we are looking for are in those first and fourth quadrants where the asterisks are. All right, so let's go ahead and do an example computation of arc sine of negative 1 over square root of 2. Now, one way of understanding this is making it look like more the way we think about it. Because remember, the way we think about arc sine of negative 1 over square root of 2 is we're thinking of it as an angle that we put into the sine function. So I'm going to make it look more like an angle by calling it theta. So theta is equal to arc sine of negative 1 over root 2. And we want to figure out what that theta is. Now that we have this equation, and note that theta and arc sine are both angles, let's go ahead and actually try to put them into the sine function to see if that helps us understand it better. Because one thing I want to sort of help you start practicing is whenever we have an inverse function of a function we understand, the inverse function we don't understand very well by itself, but we can understand it better through the function that it came from. So if I were to put both of those angles into sine, on the left-hand side, we're just going to get sine of theta, which looks fine. And on the right-hand side, we're going to get sine of arc sine of negative 1 over root 2. Now, the left-hand side looks fine. There's nothing more we can do about it to make it look more pretty. But the right-hand side of that equation, that sine and arc sine, remember, they are inverse functions, which means they cancel each other out. So when I take the sine of arc sine of something, those sine of arc sines are just going to disappear to cancel each other out, and we end up with sine of theta equals negative 1 over root 2. And that's an equation we understand a lot better than theta equals arc sine of negative 1 over root 2. So let's see if we can actually figure out what that angle theta is going to be. Well, remember, we're looking at our circle, and the first and fourth quadrants are the angles that we're looking at. That's where theta can be. And first of all, let's see if we can figure out what quadrant we're in. Now, sine theta, that is going to correspond to the y-coordinate of the unit circle. And remember, sine of theta equals negative 1 over root 2, which is a negative number. The only place that we can get negative y-coordinates on the unit circle is going to be in quadrant 4. So not quadrant 1. We're going to get in that little asterisk place down in quadrant 4. All right, so let's look at what the right triangle is going to look like. Well, it's going to be a right triangle in that fourth quadrant, and the sine of the angle theta is equal to -1 over root 2. That means I'm probably going to want to make the radius of length root 2, and in order for it to be -1 over root 2, the y-coordinate has to be -1. So our y-coordinate is -1, our hypotenuse is root 2, sine of theta equals -1 over root 2. Everything's looking good so far. Now, if I really want to understand how that, what that right triangle is, I probably should figure out the third side. I don't know what its length is yet. I'm just going to call it a. The nice thing is our Pythagorean theorem can help me figure out what a is. I get a squared plus -1 squared equals square root of 2 squared, which means a squared plus 1 equals 2, which means a squared equals 1. And if I take the square root of both sides, I got to be careful. A could be plus or minus 1 as far as I know. We got to be careful about those things. But if I'm actually looking at a, it is the x-coordinate of that triangle. That x-coordinate is a positive value of x because it's to the right of the y-axis, and that means that a has to be +1. So I'm going to go ahead and put that in. Now I got to take a good hard look at that triangle and ask myself, do I recognize it? Well, yes, of course we do. That's an isosceles right triangle. Both sides of that triangle have length 1 that are not the hypotenuse. So we have two sides of length 1, one side of length square root of 2. We know what that one is. If we have theta is less than 0. We have an isosceles right triangle. That means theta has to be -pi/4. -45 degrees if you're a degrees person, but we're doing radians here. So our theta is -pi/4. Remember, our theta was also equal to arc sine of -1 over root 2. So if we have theta is arc sine of -1 over root 2 and theta is equal to -pi/4, we can put those together to get arc sine of -1 over root 2 is equal to -pi/4. So hopefully that computation gives you an idea of how to do those computations. We've got two sets of in-class activities to work on. One is looking for what the domain and ranges of the inverse trigonometric functions are, not just the arc sine, but the other ones as well. And then there's another set of activities where you're going to do some inverse trigonometric function computations. Those are on 2 PDF files included with this video. Hope those go well for you.